Hello, welcome to our new unit looking at the group 2 elements. To start off this unit, we're going to focus first on the trends in the group 2 metals, looking at understanding and describing the trends in the physical and chemical properties of the group 2 metals. Our learning outcomes we're addressing just below there. So we just finished our previous unit, and that was focusing on periodicity. So that's as you read across a period, the trends from the left to the right. Now we're going to be focusing for this unit and the next unit looking at specific groups, so specific columns on the periodic table where you can group the elements in this column together. I guess thus a group. We're starting with looking at the group 2 elements, which are known as the alkaline earth metals. So there they are there, from beryllium down to radium. They're named after the oxides as they are alkaline when combined with water. We saw this in our previous one when we were looking at the oxides of the group 2. We were looking at magnesium oxide, and we saw how that would make a hydroxide and alkaline in water, so thus an alkaline solution. We're going to look at those reactions again, but looking at them with respect to the rest of the group 2 elements in this unit. So yeah, alkaline, as they combine with water, they form a alkali solution. And the earth part is a historic term applied by chemists way back in the day to these non-metallic water-insoluble compounds that are resistant to heating. So the earth comes from the oxides of the group 2, but when they found out that they could just get the metals by themselves, this term, this alkaline earth metals term, just stuck, like many things do with chemistry. These old terms just stick around, and that's just what they get referred to as. These are in the S block. S block being group 1 and group 2. They're going to have 2 S valence electrons as the subshell electronic configuration for their valence shell. So, for example, beryllium 2s2, magnesium 3s2, 4s2, 5s2 as that valence-most shell. Because they have the same valence electrons, or I guess the same orbital subshell as the valence electrons, they're going to have similar chemical reactions, similar chemical properties. But as we're going to see, their reactivity is going to change with respect to where they are on the group as well. Chemical properties largely depend on the valence electrons, so we'll observe similar chemical properties as we go down the group. But let's start off by looking at some of the physical properties and the trends we observe. First, with the atomic radius. We're going to compare the metallic radius, as the group 2 are all metals. So when we were looking at comparing the radius for our periodicity going across the period 3, we were looking at the covalent radius, but as these are all metals, we can compare the metallic radius, which is exactly what it sounds like. If you have a metallic lattice where you've got your cations all forming the structured lattice with the delocalized electrons, you can measure the point between the 2 nuclei, and then half of that is going to be the metallic radius. So let's have a look at the trend that we observe in the metallic radius for our group 2 elements. It looks like this. Pretty obvious there that we have a general increase as we move down the group. And this makes sense because we know as we move down the group, we're going to be adding an extra principal quantum level each time we move down the group. If we go back to the periodic table here, we're going to have our beryllium having the 2s as the outermost shell. Magnesium going to have 3s, 4s for calcium, 5s for strontium, so on and so forth. So we can pretty clearly observe that, you know, if we've got 2 quantum levels, and then if the next one down has 3 quantum levels, the next one down has 4 quantum levels, very obviously we're going to have an increase in that atomic radius. Now, leading on from that, let's look at some trends in the ionization energies. This is something that we've looked at a while ago, so it will serve as a good recap. Based on what we know about the factors affecting ionization energies and the trend in atomic radii, what would this trend be? Well, it looks like this. We see a decrease in the ionization as we go down the group. So we've got the atomic number down the bottom here. So we've got beryllium as atomic number 4, magnesium 12, calcium 20, so on and so forth. And we can rationalize this for the same reason that we see an increase in the atomic radii. If we are adding an extra quantum level each time we go down the group, the valence electrons are further away from the nucleus, Therefore, that electrostatic attraction is weaker between the valence electrons and the nucleus because they're further away as we go down the group. That means that it's going to take less energy to remove the valence electrons, and therefore they're going to be easier. It's going to take less energy to do that. So we see a decrease down the group. The valence electrons is a principal quantum level further away from the positive nucleus that is holding it. So the electrostatic force of attraction as it goes further away becomes less, therefore less tightly held, therefore less energy to remove it. If we draw that on our diagram over here, we could imagine if we've got our two s electrons in the valence-most shell, they're going to be closer than the one which is a group down, which is an extra quantum level. That's going to be further away they are, the less tightly held by the nucleus they will be. Let's look at some more physical properties here. What about the melting point? What causes the melting point value? Well, these all being metals, it's going to be the strength of the metallic bond. When you are melting something, you're going from a solid where you've got a very uniform, fixed volume, fixed shape. The lattice has the three-dimensional arrangement that has a strong bonding between the particles. As you go to the liquid, you disrupt that lattice and you go to that liquid phase where you've got a fixed volume but no fixed shape, so the particles can flow freely over one another. So the melting point is going to be dependent on the strength of the bonding between the metals, between our group 2 metals in this case. So thinking about that and thinking what we just saw about atomic radius, what do you think the trend is going to be? I'm going to put a graph up here, see if it's what you thought. Generally, we see a decrease in the melting point as we go down our group 2. Again, we've got our group 2 elements there. Now, the bond is between a positive cation and the delocalized electrons. So the more delocalized electrons, the stronger the bond is going to be because the cation will be more charged positively and there'll be more delocalized electrons. However, they're all group 2, so they're all going to contribute the same amount of delocalized electron to that metallic bonding lattice. However, what we need to consider is the distance between the nucleus. If I draw my metallic bonding model again, distance between the nucleus and these delocalized electrons. And it's the same thing that we saw with the ionization energy really, where if we increase the distance, we're going to decrease the electrostatic force of attraction. So as these cations become bigger, more quantum levels as we go down, the nucleus is further away from the delocalized electrons. That makes a lower force of attraction. That means that it's easier to disrupt the bonds. We do see an anomaly here with magnesium, but there's no simple or quick explanation for that, and it's not something we need to be concerned about right now. So let's just move quickly forward. Final one, what about densities? You might want to have a think about this one. If we have density as a measure of mass per volume, let's consider what we're going to change as we go down the group. Well, we're going to change both of these things, aren't we? As we go down the group, they're going to become heavier because we've got higher atomic numbers, higher mass numbers for the ones that are further down the group. We're also going to change the packing arrangement because they become bigger as they go down the group. And we see a trend like this, where we have a decrease in density up until our calcium, and then a big increase in density as we go down to strontium and then barium. So I guess you could summarize that as a general increase, but really we've got a bit of a decrease and then an increase. And this all has to do with how much mass you can do per volume. For the first few, we got real small ones, so it turns out that, the packing of it, if you can have smaller ones more packed in a given volume, that's going to make them denser, and that's why we see that general decrease to begin with. For the first few, the tight packing of the small atoms make them denser, but then as we go down, it turns out that the heaviness, the mass of these much bigger strontium and much bigger barium makes them much denser. Even though they are bigger, they're just much heavier atoms, which will increase the density there. Excellent, so there are a few physical properties that we can justify based on what we know about the atomic structure, I suppose. Let's now look at some chemical properties. Like I said earlier, they're all going to have these 2 valence s electrons, so they've got similar chemical properties, but we do see trends going down that group in the chemical properties as well. Let's have a look. What do we have here? So they can be oxidized when they react to lose these 2 electrons in the valence shell. If you think about it in terms of the octet rule, it's going to be easier for them to lose 2 electrons than to gain 6 electrons. So these are going to be oxidized, where we're going to have something like calcium. Let's say we got a calcium solid that can lose those 2 electrons to form the Ca2 plus ion and the 2 electrons like that. If they are able to be oxidized, it means that they are good reducing agents. If we think back to our electrochem topic, if we have a redox reaction, something needs to be reduced and something needs to be oxidized simultaneously. Redox can't happen, one can't happen without the other. So if we have a species where we're losing the electrons, they're the electrons that are being gained by the thing that is going to be reduced. So if our calcium can be oxidized, that means it's going to be a reducing agent because it can supply the electrons to the thing that will be reduced. It is an agent for the reduction of the other thing. It itself is oxidized. Let's have a look at what we knew about the first ionizations, where we got this general trend where the ionization energy, it takes less energy to ionize them as we go down the group. Here's a question. I want you to pause, write down an answer, and then check. What do you think? Decreasing ionization energies, would this make them more reactive or would this make them less reactive? And why do you think so? You can check that now. The group 2 metals are going to get more reactive as we move down the group. Let's think about this. If it's easier for them to lose electrons, then they're more readily going to react, because as we saw over here, that is how they react. They react by losing electrons. So if it's easier for them to lose electrons, they're going to be more reactive. Takes less energy to remove the valence electrons, therefore oxidize them. The extra quantum levels and higher shielding is a bigger effect than the increasing nuclear charge. So if we think in terms of ionization energy, we said the things that affect ionization energy is going to be the number of quantum levels, the shielding, and the nuclear charge. And whilst you'd be correct to say that, well, the elements further down the group are going to have a higher nuclear charge, so potentially that could make them harder to oxidize or harder to be ionized, oxidized in our specific case of the group 2s. It turns out that the effect of the quantum levels and also the shielding, because they kind of go hand in hand, outweighs the effect of the increasing nuclear charge. So less energy to remove those electrons makes them more reactive because it's easier for them to do so. Let's illustrate that with a reaction with oxygen. We can form white solids of the group 2 elements. They burn in air or oxygen. Here's a question you can have a go at. Write 2 equations showing the reactions of magnesium and calcium with oxygen to form a metal oxide. So you know what's being reacted, you know what's forming. See if you can write in a reaction with states as always, and predict which one would be more vigorous based on what we just said. Let's check the answer. We would have got 2 reactions that look like this. Straightforward, we're just reacting our metals with our oxygen gas to form the metal oxides, and we simply got to balance that. Now, we looked at the fact that as we go down the group, they become more reactive because the valence electrons are easier to get rid of. So our calcium one would be more vigorous than our magnesium one. Now, our burning magnesium is quite a brilliant reaction. You get a large amount of energy released, and it actually releases it in the form of UV light. So you can't look directly at it. If you ever see a demonstration of this, you got to look in your peripheries because UV light can do damage to our retinas. That's why we're told not to look directly at the sun, because that would damage the retinas, and that wouldn't be good. That wouldn't be good for our health. Okay, so we can see how we can make the oxides. We have looked at the oxides of magnesium in the previous unit when we were looking at the periodicity of period 3s, and we said it's basic in nature because you make the hydroxide, metal hydroxide with water. This is the same with all our group 2 oxides. Calcium oxide reacts vigorously with a small amount of water to produce a solid product. Write an equation for this reaction. If you want to pause, check it. Again, pretty straightforward. We know what we've got. Calcium oxide plus water to produce a hydroxide. It would look like this. Form a solid product. So we have calcium oxide in the solid plus water goes to calcium hydroxide, which is also solid. All balanced there. Now, these hydroxides, these group 2 hydroxides are alkali because when they are put in water, they can be soluble, different degrees of solubility, but that means that we can disassociate them into hydroxide ions and into our metal ions. So in the case of our calcium hydroxide, which is going to be solid, If this is slightly soluble in excess water, we would form Ca2 plus ions, aqueous, and OH minus ions, also aqueous. So these OH minus, this is the thing that makes the solution alkali. We discussed the Bronston-Lowry definition of acids and bases in a previous unit as well. And we said that a Bronston-Lowry base is something that can accept a proton, and that's exactly what these hydroxides can do. The base is soluble in water, as we have the aqueous form here, it is an alkali. So our hydroxides are going to make the solution alkali because it dissociates to form these hydroxide ions in the solution. Yes, that's what we see there. So if we add aqueous, we add the water, dissolve it, we get that. Now, the solubility increases going down the group. And if we have more soluble metal hydroxides, it means we have a higher concentration of the hydroxide ions. Because the more soluble something will be, the higher the concentration of this, because this will dissolve more if it's more soluble. So if we have a more soluble group 2 hydroxide, we're going to have a higher concentration of hydroxide ions in solution. Therefore, the alkalinity is going to increase. So just to go back to the namings here, the group 2 oxides traditionally called the alkaline earth metals. As we can see here, they form alkali solutions when they are in water. And then the earth metals came from the discovery of these oxides. And then when they found, or they managed to get just the single metal elements, I suppose when they discovered the single metal elements, it just stuck with this name of the alkaline earth metals. So we can summarize this as a general reaction for our group 2 oxides with water by having the oxide reacting with water to form the hydroxide and thus an alkali solution. All right, here's a question based on that general reaction. Can you write a reaction of strontium oxide with water? Pause now, give it a crack. Here is the answer. It is simply going to be the strontium oxide with water will form the strontium hydroxide. Excellent. Final thing to look at for today's lesson is the idea of a flame test. You can do a qualitative analysis in chemistry, qualitative where you are getting information about the substances you're experimenting with, as opposed to a quantitative, which has to do with measurements of a mass or a volume or some sort of numerical data. Qualitative analysis is where you can do tests to get the identity of an unknown, and you can do a flame test with the group 2 metals because they have quite characteristic flame colors that are due to the formation of the 2+ ion and all to do with the electrons within those ions. So we see calcium 2+ has a very characteristic orange-red color flame. Strontium 2+ has a scarlet red color flame, so a bit of a deeper red there. And then our barium 2+ has a green flame. And that's the end of our first lesson into our group 2s. What have we done? We've described the reactions of the elements with oxygen, water. We haven't looked at dilute acids. That will be in the next lesson. We've described the behavior of the oxides, hydroxides, and carbonates with water and dilute acids. Again, a lot of that will be in the next lesson too. The carbonates and the dilute acids will be in the next lesson. We've interpreted and make predictions from the trends in the physical and chemical properties of the elements and their compounds. Task for this lesson, pause now, work through those columns. You beauty. That is it for the first lesson into our group 2s. I'll see you on the next one. Have a great day.